So my focus today is going to be around Appendix 1, which looks at the detailed design of a timber frame mid-rise building. Now, just as a bit of a recap, what is Design Guide 50? And for those of you that weren't in Adam's webinar last week, this is partly for you guys. So Design Guide 50 focuses on the mid-rise design considerations for both timber frame and CLT as a solution for a mid-rise building. But importantly, those principles, as they relate to CLT, could also be equally applicable to other mass timber systems such as LVL, Unilam and nail laminated, less significant in the market, but still viable options for different types, different projects, different times. The guide also really usefully, although it's a guide for structural engineers and structural engineering, provides a background across the key performance requirements and the design approach. And the key performance requirements often for these mid-rise structures are actually not the structural performance requirements, but framed around fire and acoustics, which Adam touched on last week. And as I go through this webinar, looking at the detailed structural design for certain elements, I will keep coming back to how we then think about the fire and acoustic performance and how that influences our decisions structurally. The design guide has three main sections: the body of the document, and then two appendices. Appendix 1, which I'm talking around today, which is the detailed design of timber frame solution, and then Appendix 2, which Nick will talk about next week, which is the CLT solution. So today we're going to expand on those timber framed detailed calcs. So who is the guide aimed at? Well, I guess you may fall into one of a few criteria. You may be familiar with working as a structural engineer on mid-rise buildings, but maybe not so familiar with timber, either as timber frame or as mass timber systems. You might be familiar with timber construction, timber frame, say for Class 1 buildings, but you might be looking to work with your regular partners, contractors, builders or developers, moving up into the mid-rise scale. You may be new to this field of timber framing, timber engineering and mid-rise buildings and just looking to expand your skills. And interestingly, the guide is framed to target engineers, but actually anyone involved or interested in upskilling in the mid-rise timber building space can get something from this guide, particularly the main body of the document. So we ended last week's webinar with a few key points. Timber solutions can be a cost-effective option for mid-rise, and developers, particularly over on the East Coast, are demonstrating that. There's obvious environmental benefits when it comes to using timber in construction. And importantly, there's a deemed to satisfy solution for fire-protected timber for buildings of any class of this scale, which is a key one with respect to the fire design and the fire solution. The DTS provides a cost-effective option for satisfying the requirements. Acoustic detailing is critical, and I'll touch on this again and again through the presentation today. And there's actually an opportunity for some really strategic decisions on prefabrication. So I'm just going to start with this before we go into, if you like, the detail of the engineering calculations. So if we were to consider a matrix of prefabrication, looking something like this, where on the x-axis we have prefabricated nodes and we're moving all the way along to volumetric prefabrication on the x-axis. And on the y-axis we're moving up from not much prefabrication to a completely prefabricated element. Most commonly, what we're talking about in this mid-rise space, although there may be some volumetric construction and there may be some stick-built construction, what we're really talking about as the sweet spot is typically around panelized prefabrication. That middle zone, those sort of 2D elements made up as either open frames, sheathed and insulated frames, and it really depends on a project-by-project basis what the most appropriate solution is. So typically, when we're talking about timber frame mid-rise, it comes with it an assumption that actually there will be panelized elements of prefabrication, wall frames, floor cassettes, and so on. A bit more about the guide and about what I'm aiming to do today in the presentation. The guide has a lot of detail. It's 250 plus pages, including the body document and the appendices. We can't hope to talk you through step by step the calculations as we've done in the appendices for the worked example. What I'm going to do today, hopefully, is set the context, kind of set a background for our assumptions and our models that we've used and drawn from different codes and standards to pull together to give what we think is the best practice guide for timber frame design and buildings of these scale, and explain a bit more about how these models work and what those assumptions are. So jumping in, Appendix 1, the front cover looks like this. And the key thing really as we move into the engineering design of these structures is to think through the design process. And so this kind of process flow document should be familiar to you in whatever building form you're working on. We've got the phase 1 prelim design, then we move to detail design, fabrication and assembly. Now, a key thing here with respect to the mid-rise timber frame solutions, and as we cover in this guide, is we step through prelim design and into the detailed design for specific elements. We can't in this guide start to draw too much about fabrication and assembly because so much of it depends on who you're working with in the supply chain, contractors, fabricators, developers, and so on. But what we try and do is talk through both the prelim design, what informs your key early decisions to make this building as feasible as possible as a timber frame solution, and then we pull out some key elements to do detailed design checks on. You notice step 2 there in prelim design, early supplier involvement, and that's critical for these buildings, especially for developer-led solutions of mid-rise that need to be cost effective. And really cost is one of the main drivers in these structures, especially if you're going for a deemed to satisfy fire protected timber solution. The timber will be used because it is the most cost effective option. So getting that early engagement from the supply chain is critical. Now, Wood Solutions have developed a model apartment building, which is 7 stories above a concrete podium. And it's this that the appendix works through doing some of the key design checks, both in terms of prelim design and then detailed design. Now, interestingly, for this exercise, as part of this appendices, we were given this building as it stands, and we then engineered a scheme to fit. In reality, of course, one would hope that as an engineer, you have some more influence over the design process and there's a chance for iterations. So there's certainly some things that we would do with this building to improve the chances, or if you like, improve the efficiency of a lightweight timber frame solution. But we'll go through these steps as the webinar unfolds. So this is what it looks like in cross section, a very kind of typical detail of modest basement, a relatively generous floor to ceiling height for your ground floor, which has a different function, maybe food and beverage, retail outlet, and so on. This is concrete. And then above that point, the timber frame starts. The timber frame plan, which is the key thing, looks like this. So there's a central core structure, core in inverted commas, a central structure which houses all the vertical kind of circulation, whether it's for services or for vertical circulation of people, lifts, stairs, and so on. So there's that central zone there highlighted, and then we've got apartments, single occupancy apartments scattered all around. I'll come back to this building a few times through this webinar, so you don't need to remember it, but this is the example building. The brief for the example building, if you like, or the design approach is expanded on more in the appendix, table A 1.0. So if when you're going through the appendix and you're looking at the calcs and the process we've gone through, you need to, if you like, back into the fundamentals of what define this example building, you can. The drawings are there presented as kind of sketch form, and this table then presents the key kind of brief requirements for that example building. I won't go through them now in detail. So we've got our building, we've got our brief. The first step then is to really get into understanding the loading. Now, this is an excerpt from a table that defines different floor build-ups. And the reason I show this is I'll show the expanded version of the table here, although the writing might be a little smaller. This is presented in the guide in chapter 4 as examples of different floor build-ups and different acoustic requirements. It's here, and it's a really important thing to understand early in the piece when undertaking a lightweight timber-framed multi-residential mid-rise building. The acoustic requirements of the floor will require some mass provision and will certainly require some isolation of different floor structures, whether it's an isolation of a suspended ceiling through resilient mounts, an isolated layer of wearing surface over the top of your timber floor, and or mass provision. So it's really important to understand the floor build-up for both acoustic and fire. So for the fire performance, it's also likely that there's going to be a need for specific encapsulation, being a structural element that holds up walls. So this table's presented there, and it gives you the fire performance and the acoustic performance of both the timber and the concrete solutions to allow you to reference back to what would be the developer's benchmark in many cases, which is to say concrete flat slab, concrete flat slab. So you can say, look, concrete flat slab performs in this way. We've got an equivalent performance from this timber solution of this depth. Therefore, in my design, I need to use this mass. I'm not going to go through wind and earthquake loading in detail, but the Appendix A does go through it in a little bit more detail than this, only to say that for this particular building, for the lightweight timber solution, the earthquake loads and the wind loads are not dissimilar. Working through the seismic design, in this case, we've actually taken structural performance and ductility as a braced frame rather than a shear wall, which is the 0.77 and the 2. So here you've got an example of the kind of way that the calcs are set out in the appendix. So we've tried to set them out cleanly and reference either assumptions or codes and standards from where we've got the relevant information. There's an ongoing discussion about the definition of shear walls in 1170.4, and actually shear walls tend to infer something that is stiffer with more flexible hold downs, such as a CLT shear wall. And by taking the assumption of braced frames in this case, we align ourselves more with the Eurocode assumptions. But even so, ductility of 2, structural performance factor of 0.77, we can see that for a lightweight structure such as this, it still doesn't generate a dominant case of seismic, and we know that we've been reasonably conservative with our assumptions there. Now, moving on to the walls. So I'll start on walls from a kind of scheme point of view, from a preliminary design point of view. I'll then move on to the floor design, looking at detail, and then we'll come back to walls again. So here we have our plan marked up in incredibly garish colours. For those of you that are colourblind, they're numbered in the table but not on the plan, which is of no use to you at all. But anyway, so we have the first step in assigning the walls through a plan like this is to say, well, where are the boundaries between individual living units, between individual single occupancy units? Because we know that they are going to have both a fire performance requirement and an acoustic performance requirement. And in some cases, if they separate a wet room or a room with a tap from another space, they will have to be, they're mandated to be separated skins of wall. Now, in many other cases, such as the acoustic performance between adjacent units, the acoustic performance requirements are set by client or BCA, and client requirements are usually insensibly more stringent than the BCA requirements. And the most cost-effective solution in many cases is a separated stud. So you can start off by marking up this plan right the way across the board to say, actually, between units, we've got separated studs. We have 2 leaves of wall, which will give us our thickness. And we'll also start to define where we can then get bracing. Now, looking at this plan, we can see that left, right across the screen, there's plenty of walls running in that direction, giving us good stability. But it's often the case with these type of apartments is that they have a view or an outlook in one or other direction, which leads to the desire to have these really kind of open ends, these open faces. And you can see that in this case, up and down the screen, there's very little structure. So we've got this kind of conflict, really, that we're trying to resolve in our heads between modest spans running up and down the page, which suit really well our floor design and our floor structure, onto walls, those walls will then benefit in some way from the self-weight of our floor. But the direction that we're hunting for stability most is up and down the screen. And those walls that run up and down the screen will not have any beneficial load from our floors which span in the same direction. And that's what the sketch on the right shows there. So you can see that where the floor spans onto a wall, we get some beneficial dead load. but where the walls are parallel with the floor span, we don't. And in this particular building, as is often the case, those are the ones that are oriented in the direction that's working hardest from a stability point of view. So this is a sketch that I've stolen from Adam's presentation, albeit flipped around 90 degrees. And so the key things here to remind ourselves about are spans that suit an efficient floor cassette design, minimize transfers, and we have a transfer at the concrete podium level, but that's moderately straightforward. So minimize transfers up and down the building, and keep the detailing and keep the provision of walls simple throughout. So that's the kind of preliminary considerations for wall design. We need to think about where we have load-bearing walls, where we have walls that are non-load-bearing but will be part of our stability system, and where we have a requirement, either acoustically or otherwise, for separated skins of walls. Floors. So we've got our floor span direction, and it's a reasonably modest floor span of around 6 meters. We've got many options to achieve a 6 meter floor span, which I'll go into in a minute. But a key thing we need to think about is how transportation links to our floor spans. Ideally, we can have cassettes that are continuous over 2 bays, gives us a lot of benefits, but we need to try and marry that with whatever our transportation requirements are. Something on floors with respect to acoustics is that some very enthusiastic acoustic engineers may try and request that floor diaphragms and floor structure breaks across the boundaries between adjacent units in order to get the sufficient acoustic performance. We would strongly encourage floor structures and diaphragms to be continuous as far as possible and to look for alternative solutions for upgrading the walls to achieve the acoustic performance. So where's our first port of call for prelim floor sizing? Well, Wood Solutions has a great design guide here, Design Guide 46, which looks at wood construction systems. And in there are all kinds of different lookup tables for these preliminary design decisions, which allow you to marry imposed load and achievable spans. Apologies to Wood Solutions, but here's another reference. This is a really good one from the UK. This is published by Trada. And this does something similar, albeit in a slightly more graphical form. And the thing I really like about this one is that you can see the bars of performance are shaded based on what's governing your design. And this is really, really helpful for us as engineers, because if we have something that's governed by blue, or bending in this case, which is strength performance, we might have a slightly different approach to that than we would if we had a structure that was governed by vibration performance, for example. You know, the vibration performance, which we'll go into in a minute, is subjective. And it may be that a client wants to ensure that they have a super high performance floor structure, with a very stiff response, because they're maybe marketing to clients who are used to concrete structures, for example, or very stiff buildings. Or it may be that the client wishes to push the dynamic performance, knowing that they've got a fairly accepting set of clients. Sorry, I was just checking the chat to check if audio is okay. Is the audio okay for everyone? Is the Trada guide available for download? Yes, it is. You'd have to buy it from Trada, but it is available. Okay, is the pace okay for everyone going through these slides? All good. Yeah, thanks. Okay, so the Trada guide is a really useful one for pre-scheme design. But bear in mind, this is a UK guide based on targeting the UK market. And so certain things may be different, available products, certain sizes and practices as well. So it's good as a reference, but it is just that, a reference for you to then set in the context of the Australian market. So here, that's our preliminary floor sizing. And you can see that for what we might consider efficient structures, our floors will be governed by dynamic performance. So I've said here floor dynamics likely to govern. Actually, if I was doing scheme design on a reasonably spanning floor that I was trying to make as efficient as possible for a mid-rise building, my first check would probably be a dynamics check. And within that dynamics check, there's a hierarchy of checks that you can do. So usefully, the the detailed design from a prefabricated cassette solution is likely to be by the specialist fabricator. But that doesn't mean as an engineer that we shouldn't have a very, very good idea about what we're expecting in terms of member size and distribution of members before it then goes to that specialist for detailed design. So our hierarchy of checks, which are expanded on in detail in the guide, effectively start with a check which looks at deflection under a point load and checks that deflection is within a certain limit. And that is really a check to say, well, how stiff is my floor under static load? The second one is a dynamic check to look at the frequency response. And then the first step with that is to say, is my frequency above a certain value? But then there's a second check where we look at the combined ratio of the frequency versus the static stiffness. And we have some acceptance criteria for that. But the interesting thing about timber floors is that being lightweight, they can have relatively high frequencies because they're lightweight. But because they're lightweight, they may be less stiff than heavier weight things. But also, importantly, because they're lightweight, the accelerations can be our biggest problem. And from a dynamic point of view, the acceleration is what we perceive. So an acceleration check is the most thorough, albeit the most difficult, but the most thorough check we can do on a timber floor structure. So here's the hierarchy. Eurocode 5 point load check, dynamic frequency check from the CLT handbook, but the maths is the same wherever you get it from. And in this case, it's presented as EI effective, and that's to cover off the case that you don't have an EI that you've calculated from your solid joists or from your I joists, but you've calculated an EI effective based on a gamma model or something similar for a CLT panel, as it's taken from that handbook. But if you have EI, you just use EI stiffness. And then we have the the FPI Canada acceptance criteria, which is your frequency divided by deflection under 1 kilonewton point load greater than 13. And that seems to be a reasonable check. And these are expanded on in detail in the guide, so I'm not going to go through an example now, but just wanted to explain that there's this hierarchy of checks. And to be perfectly honest, if I was pushing a floor hard to try and make it as efficient as possible, I might step through these checks in order, but I would always do all of them rather than missing off the final check, which is this acceleration check. It's the acceleration we perceive, and the acceleration that, being a lightweight floor, is something it's particularly susceptible to. One thing we have been doing on the side, this is a bit of a tangent, I have a few of them, I apologise. You can get really good quality apps for free for smartphones which allow you to capture frequency response from the accelerometers in your smartphone and then download them as a CSV. And so wherever possible, we've been capturing data from as-built floors to try and help understand what frequency you actually end up with, and more importantly, what we can expect from damping. And so if you're working with a developer that says, well, this floor's not quite as I expected, find out what the detailing is, find out what the kind of floor structure is. Is it a solid diaphragm? Does it have aerated concrete blocks, for example, that just sit on the joist? How much blocking is there? What are the floor finishes? What's the ceiling? And then capture the data as someone's walking around. If the developer says this isn't what I expected, find out what the frequency response actually is, what the damping is, and start to chart it back to some of these acceptance criteria, because we can certainly do a lot as an industry to start to build this kind of body of information. Here's a typical spreadsheet I might use for some floor design, in this case a solid floor, but the theory is the same. On the left, we have a strength check, which is absolutely fine, all the way up to 8.4 meters. This is a really great hardwood. Then we have in the middle there a static deflection check against some normal serviceability criteria, span over whatever, 250, yeah, okay. And then we start to get to the frequency check on the right. And this is based on the FPI acceptance criteria. And we can see here that is definitely governing what spans we can achieve with this floor. So in terms of hierarchy of calcs, dynamic check, then static deflection, and then a strength check at the end. Looking at walls, we've got options here of wall framing and therefore wall performance. So most commonly, we've got that central case where we have stud frame walls with nogs. So in the minor axis, we get we get restraint at the mid-height, and in the major axis, we get buckling about the full length. But more and more, as we move to prefabricated wall panels, we get the condition on the right there where we have sheathing over the whole wall panel, at least on one side. That's done for many reasons, including robustness of the prefabricated frame. And so we need to think about that within our stud design. The guide takes you through all the considerations and all the factors for use with AS 1720. So stud design is conducted entirely to AS 1720. Design, as far as possible, is done to 1720. And where we've pulled models or references from other standards, we've been quite explicit about that. So all the design assumptions about, for example, effective length, levels of restraint, and so on are calculated through in quite transparent detail. And what we've then done is we've then looked at actually matching different stud grade against the different performances required up the building. I'll come in a second on to stud optimization. But fundamentally, for the example building that we've worked through, what we've looked at is 90 by 45 studs at 600 centers, 2.61 meter stud length. And for optimization up and down the building, we've varied numbers of studs laminated together and stud grade. So here you can see, for example, interesting thing to point out is that with row C, when we go to work out our stability factor, it's based on the ratio of stiffness over strength. So we can see that for K12 with LVL, we've got a lower value than we have for the MGP grades because its stiffness is so much higher ratio over strength compared to sawn softwoods. So LVL is still a very high performing product, but we do get slightly punished on our K12 value there. So stud optimization, what's the approach? Well, there's lots of different approaches to stud optimization. And again, this is critical with that early supplier involvement to really understand what is the most efficient way of optimizing the studs for a particular builder or fabricator that you're working with. And it may be that stud centers remain the same throughout the building. And by aligning stud centers, what we're doing is we're avoiding transfers at intermediate stud heights through wall plates. So we're minimizing the bending on the wall plates. Or it may be that actually the most efficient thing is to increase stud centers. And here's an example from a Timber Truss Victoria. LVL studs at quite close centers at the lower level of a mid-rise. And if you change stud centers up and down the building, you need to think about how then that axial load gets transferred through your wall plates from one floor to the other. And I'll just expand on that in just a second. Looking here at the holes though, in the guide, we've got a table where we provide a first pass sort of sense check on hole sizes that you may or may not need to be concerned about. So looking at the walls again, what we've done is we've set out for the different stories what stud design you would look to as a minimum for this seven-storey structure to get the performance that we need, based on all the counts being conducted to 1720. So for stud design, we haven't had to look outside of Australian standards for either the models or the design steps that we need there. Now, talking about transfers through floor plates, we've got different types of framing here. So we've got platform framing on the left, semi-balloon in the middle, and balloon on the right. Now, the advantage of balloon framing and semi-balloon to a certain extent is that we are minimizing the amount of timber that's loaded across the grain. And what we know about timber is that parallel to the grain, trees being, the wood fiber being more or less like a bundle of straws with the grain running up the tree. Along the grain, we've got a relatively stiff and strong load path compared to across the grain. And the more material in our vertical load path that we have across the grain, the more we need to be concerned about axial shortening. And this plays into those decisions about stud optimization. So let's say that for stud optimization, we want to change stud spacing and stud distribution at every floor. But in order to do that, we need to have very deep transfers at each floor to distribute the load around. We're increasing we're increasing the perpendicular to grain load at each floor. Therefore, we're going to increase the amount of axial shortening we have. So for platform framing, for example, we have our stud walls, the floor cassettes get dropped on top, and then the next wall gets dropped on top of that. We have 2 wall plates and an entire floor cassette at each system loaded across the grain. I'm going to talk more about axial shortening in a second, but I just want to tie this back to our decisions on stud optimization. If we have platform framing, we can potentially use the strong backs for the floor system, which are the elements that frame the ends of the floor cassettes, to distribute the load if our studs don't align from one floor to the next. If we have balloon framing, studs have to line up. If we have semi-balloon, then we end up loading what are minor axis direction of our floor plates to try and distribute the load around. So that decision around stud optimization is really critical as it relates to the overall framing system. The disadvantages of semi-balloon and balloon is that we end up generating eccentricities in all of our studs. I hope that makes sense. So now that's a perfect segue onto axial shortening. As our buildings get higher, we need to pay more and more attention to fundamentally understanding the load path through our structures. And our golden aim is to minimize material loaded perpendicular to the grain in over the height of our structure. So strain is proportional to stress. Yep. Large cross-sectional areas, lower stress, lower strain, so lower shortening over the building height. And so the conclusion to that, or I guess the output from that, is that we get more shortening in stud frame construction than we do in mass timber panels, just because there's more material present in our mass timber panels. On the right there, you can see a classic, which is a piece of plumbing where the stud, this is an upper floor of a mid-rise building, the stud structure is shortened, the soil vent pipe hasn't, as it runs all the way up the building. There's not been enough clearance, and the stud has just sheared that connector off. So our cumulative shortening, adding up through the height of the building, is a sum of the elastic strains and the creep strains and the shrinkage of all the elements parallel to grain and perpendicular to grain, plus the closure of the joints. This is expanded on in a lot of detail in the guide because it's a really critical thing to get right. And by understanding it now, when you're making those early decisions, you can then make the right decisions about what framing solution you're going for. So I won't pick the eyes out of this in detail, but what I will say is when we're looking at shortening parallel to grain, the important things to consider are our stud area, of course, long-term creep, so we're looking at a J2 factor of 2. We've got our stud length to consider, but importantly here, we think it's fair that instead of taking the average MOE for the particular grade from 1720, that we acknowledge that this can be and may be a conservative process if we layer each of these elements on each other every time. So it's fair to take a 5% increase on the average MOE, knowing as we do that the sawmills use MOE as a grading parameter and typically aim 5 to 10% higher than the design value. So what we're saying is you can take 1.05 times the average MOE from 1720 and use that. So that's shortening, elastic shortening parallel to the grain. So all of your studs parallel to grain at the height of the building. We then have shrinkage parallel to grain. And shrinkage will occur. The sawmills will produce their timber to a certain moisture content. In service, we can expect a typical change in moisture content of something like 4 to 8%, depending on where you are in the country, the type of heating or air conditioning that you have, and what kind of moisture content the building gets exposed to during construction. Now, shrinkage parallel to the grain is far lower than shrinkage across the grain. Shrinkage across the grain might be 5% for a 13-point change in moisture content, and we can expect a 40th of that parallel to grain. So you can see here 0.00096 per change in moisture content. So it's very, very small, but for a very tall building, it can add up. More critical is perpendicular to grain movements. And so we can work out a bearing area, both on the surface of our plates and through the depth of the plates. And we need to not think about a minimum criteria to be exceeded. Here, if you think about it in terms of minimum criteria, you just say, well, take the minimum area of either the top or the middle. But actually, both criteria need to be satisfied in order to get that shortening or that kind of compression through the plate. So that's why for this term, it's the maximum of those first two values and the minimum of the second two values. So what we're looking to say is that you need to exceed the criteria of both that intermediate plane and the top plane to get significant shortening through the depth there. So shortening perp to grain in the plates, this is what the diagram looks like. The other elements that we have for shortening perp to grain are the joists through the depth. Again, we have a J2 of 2. This is a creep. For E, for the perp to grain modulus, so we obviously have MOE parallel to grain, which is the grade value that we said we'd take a 5% increase on. For this one, we're taking around about a 25th of that. So it's far more flexible across the grain. That 25th includes some allowance for saying actually there are some knots there which are actually quite stiff. If you were to do a clear sample specimen just looking at the wood fibre, it'd be something like a 30th. So hopefully with this explanation, when you go through these steps, it will give you the background to work out, or to help understand what's going on here. So we've got the plates. We also then have any floor structure if we've got platform framing, and that might vary. It might be a solid joist. It might be a continuous joist where we have a different area to consider, or it might be if we've got I-joists or something similar, there might be a different area to think through. We then work through those steps for each of those different elements for the perp to grain joists, very similar to the wall plates, but with different areas. And we then not only calculate the elastic shortening of those, but again, we've got the shrinkage to consider. And in this case, it's around about it's around about 4 or 5% over 13-point change in moisture content. So that gives you your unit value, which you can then work out for something that might be a 4, 5, 6% change in moisture content in service. We found 6 to be a good value, but we need to just test the range to see how sensitive we are here. Closure of joints. We found that something like 0.2 millimeters at each joint is a reasonable assessment. When timber elements are produced in a mill, when the solid timber elements are sawn, they're produced to a tolerance that allows them to be slightly bigger but never smaller. So we need to also review through construction whether or not we're cumulatively adding up our over tolerance, and we need to review as we build. And the closure of joints is going to really depend on the detailing and the quality of the prefabrication as much as anything. So this is stepped through in a lot of detail in the guide because it's a very important concept for both stability, for both timber frame and CLT. And then we end up with a value where we can look at the significance of each of those different components per floor. So we're looking at roughly 6 millimeters of floor of axial shortening. Why is this a problem? Well, it's potentially not a problem. We just need to understand what it is. But we also then need to detail all the interfaces with the facade, with the lift cores, with everything else to acknowledge that we have this movement. Timber's not unique. Concrete moves, steel moves, all of these different commonly understood construction elements move over time. Timber's the same. We just need to understand how significant those different components are. So this is a typical example. It really varies on detailing, but this allows you to sort of understand how significant the perpendicular elements are compared to the parallel for mass timber and lightweight. And you can see the perp to grain occupies about 60% of the movement, you can see there. So we need to understand the shortening, and we need to also review and monitor building movements during construction for some of the larger scale timber buildings that have been built, such as Brock Commons, for example. Discrepancies on the predicted. So first of all, movements were predicted, details were developed to accommodate those, and then during construction they were monitored and discrepancies were dealt with shims and with modifications as we go. Okay, jumping into lateral system. Here is our building plan again with a provision of shear walls. So for the case of this appendix where we've worked through the detail, what we've said is let's look at sheathed shear walls. So lightweight timber frame studs with plywood sheathing, just as you would take from 1684 for a resi house. And we're looking at providing those in units of 600 mil, which match with plywood sizes. And we're looking through this building plan where we know we have double leaves of walls, where we can then get 2 leaves of sheathing. And that's what this plan does: 3/6, 4/2, and 5/4 lengths distributed around the building. Now, this is This is not a uniform stability system. It's pretty much symmetrical, but it's not uniform. So what we have to do is calculate how much force ends up in each of our different stability elements, because they will have different stiffnesses. The stiffer ones attracting more force than the less stiff ones. So to do that, because we have a mixed system, we need to calculate what our panel stiffness is to work out the distribution of load. And in the guide, we've done this by hand because, well, not because it was difficult, but because hopefully it sets out the theory behind it. So we're in the middle here. We're not looking at a core on the left. We're not looking at a moment frame on the right. We're looking at a provision of walls here. And actually, to ram that point home, even where we have something that might resemble a core, such as the element on the left, we're still really looking at a collection of walls. We're not saying, when it comes to the timber frame solution, that we can actually build and fabricate boxes or compound elements of cores. We're looking at discrete walls, each of which work in one of the orthogonal directions. There is detailing, and there are practices around the world where they make the core out of concrete or something similar. This is Brock Commons, not a lightweight timber frame solution, but a really clear image of cores and timber. And we do have the relative stiffness to think about. So if we do have a concrete core in our building, there's a good chance it will attract the vast majority of the load compared to any timber bracing elements that are in the mix. So looking again at this plan, we've got this provision of bracing walls. What does this look like from a detail point of view? Well, it's effectively a stack. We've got a stack of these walls, each on top of each other. The individual walls then work together to contribute to the whole. Conceptually, we've got something that looks a bit like this. I'll let you digest this in detail after, when you've got access to the slides. But ultimately, in each of the three cases, we have the same overturning moment. It doesn't really matter what it is. I've just put numbers to it instead of needing to worry too much about the algebra of it. But we have some overturning moment. And in the first case, where we have a full kind of compound composite stability system across the whole width of the building with shear flow across each of the joints, we have a certain provision requirement for hold down. In the second case, where we have separate walls over 1/3 of the width, we have 3 times the number of hold downs, each of which require the same capacity as the compound one. And then we have the kind of hybrid stacked case, which is actually commonly the method adopted in North America, where you might see reasonably modest hold downs through the footprint of the building and then some whoppers on the outside. It's this kind of compound approach. And the reason why we're trying to keep a close eye on the hold downs is that achieving high capacity hold downs is an expensive thing to do. So how do we work out panel stiffness? The guide takes us through this in a lot of detail. We've embraced a model from the Canadian design standards, CSA 086, where they look to combine considerations of panel deformation based on the strain of the edge studs in tension and compression, panel shear based on the sheathing material, fastener deformation between the sheathing material and the studs, tie-down extension, and then some consideration of shear deformation at the base based on the stiffness of your shear connection at the base there. The maths behind it is all explained, and each step is stepped through in detail. And then for completeness, we've referenced the model in C086 back to other models, so other standards based on the fundamental model of C086. So if we consider those characteristics of stud extension, panel shear, nail slip, and tie down, and we apply that theory using values from different design standards, you then get a panel stiffness for each of the different standards. And we've done that for both CSA, the Canadian standard, Eurocode, AS 1720, using all the values from there, and then reference that back to AS 1684 bracing, using an assumed deflection limit to say it's governed by deflection. And you can see that in the world of predicting stiffness, these are virtually the same. Stiffness prediction of particularly fasteners and timber is a very tricky thing. And these models are all very, very close. So diagrammatically, this is what we're talking about. Displacement of the connections, shear of the sheathing, sliding of the rigid body, and rotation of the rigid body. And if we work through that in detail, we can see here for 2 different cases, and I've just picked 2 cases to show the significance. So panel shear accounts for around about 40% of the shear distribution at the top of the wall, and that can be increased by increasing your panel thickness, plywood thickness, for example. We then have nail slip, 28 and 32% respectively in these two, and again that can be increased by putting your nails closer or increasing nail diameter. And as a starting point for detailing sheathing walls, you can't go much wrong with the standard practices that are described in AS 1684, and then upskilling that, because you know that carpenters and supply chains are familiar with working to those. And the interesting one here is the yellow, which is the tie down, 3% and 15% respectively. Just wanted to highlight something here. The one on the left has a tie down that's the full wall height. So that detail that you see as standard, where you have the threaded rod that goes all the way from one floor to the next, because it's a very long element, you then get a lot of strain in it. Whereas if we can detail it so the tie downs just go from floor to floor through the floor plates, then we can limit that movement at the top of the wall. But nonetheless, this model, as it's explained in the guide, takes you through step by step and allows you to then calculate from first principles as you need to panel shear. Or, as you can see from the previous slide, taking the values from 1684 as a capacity and assuming that relates to a deflection limit, which is explained in the guide, provides a good starting point for concept design. Now, diaphragms are important. And what we've done in the guide is we've pulled out guidance from the Eurocode 5 manual design for timber structures, which takes you through a series of detailing rules that says if you satisfy these rules, you can assume a stiff diaphragm with sufficient performance. But before I get to that, I just wanted to highlight the detail on the right there, where actually between separated wall structures, there may be a drive for acoustic performance to not have a continuous diaphragm through there, which obviously leads to a huge amount of issues in terms of load transfer and would effectively generate separated structures entirely, which would need all of their own bracing, and from a seismic point of view would all behave differently. So it's very, very complex. So maintaining some structural continuity even through those separated wall structures from an acoustic point of view is really critical for robustness as much as anything. So the guides for diaphragms in Eurocode 5, I'll just highlight the bold points there. Span to depth of less than 2 to 1, which this example building does. Less than 12 meters between stability walls, which if you're looking at a lightweight timber frame structure for a single occupancy resi, you're bound to have. Sheathing is minimum 15mm plywood or 18mm particle board. Yep. Panel junctions are nailed to a common joist, and that's really important. What you don't want is you don't want floor cassettes to come to site, and for the floor cassette connection between adjacent connections to be the weak point. Gives you a specification on fasteners and fastener spacing. So we think these are valid rules, but as the engineer, you'll need to just make that judgment on a case-by-case basis. But they seem a really sensible approach to judge whether you have a stiff diaphragm. Why is it important to have a stiff diaphragm? Well, if you don't have a stiff diaphragm, you've got all kinds of complexities with working out your load distribution between your bracing system. Because as well as working out individual wall panel stiffnesses, you then have to work out how the stiffness of your diaphragm varied along its length to then distribute load in between your stability walls, which gets really complicated, given what we know about calculating or estimating stiffnesses of systems. I will just say, if once you start to get through the detailed design of trying to estimate the stiffness of your stability systems for the purposes of load distribution, it's good practice to test a number of scenarios based on those stiffnesses. For example, if you have a combined system where you're looking at, say, sheathed walls interacting with a concrete core or sheathed walls interacting with cross-braced walls, it's good practice to say, as a base case, I'll take a stiffer assumption of the sheathing and a softer assumption of the bracing to work out the distribution, and vice versa. So you're designing for a worst reasonable case in both scenarios. WOODSOLUTIONS has a really good design guide for floor diaphragms in timber buildings, which I recommend you reference or you have a look at. And it takes you through the models for the detailed design. So the stiff Eurocode guide giving assumptions for stiff diaphragms is really good, but it's also really useful to build that confidence yourselves by running through some designs for some diaphragms and testing some stiffnesses computationally. So in this case, you have a plate element, which is your sheathing, which you need to ensure is sufficiently connected together to avoid shear deformation. We have the top and bottom chord, which needs to be connections between your individual floor elements. Then we have collectors back to your lateral stability system. This is a really clear diagram, I think. Imagine if you were trying to achieve a diaphragm with a series of floor cassettes. They in themselves are very stiff, but once it's loaded as a deep beam, you really need to make sure you have that sufficient connection between adjacent panels to make sure they don't kind of open up. They don't open up like that. On the right, you've got an image of a collector, of a kind of drag strap or collector, where you're getting the diaphragm forces back into a core. So that's the end of my summary of Appendix 1. I hope it was useful as a background to the assumptions, and will be of use when you start to then step through the calculations. As Adam mentioned at the beginning, look, we're really happy and we crave feedback. Any feedback you have on the guide, we'd be really happy to take on board and incorporate in future addendums of the guide. It's a big document, and as best practice in industry changes, we'd be constantly looking for feedback from you guys to try and incorporate what that best practice might be in the guide. But in summary, efficient structural design requires engineers to reference across multiple standards. We've tried to do the hard work for you to pull them all together into this guide. But the key thing, judgment of the most appropriate solutions based on the full range of project parameters. Structural performance is one of them, but particularly in this space, it's super critical that you also understand and acknowledge the acoustic and dynamic performance requirements, as well as the construction and fabrication. The calcs that we presented in Appendix 1 are a sample of the calcs some of the calcs that are needed, and they demonstrate feasibility of mid-rise. You know, the best solution is likely or may well be a mix of lightweight timber frames and mass timber and a blend of different things. What we've tried to do with the example is push a timber frame solution as far as we can, which we think we've pushed it just about as far as possible in the calculations. A quick shout out, if you like. I'm working with Andrew Dunn, TDA New South Wales, who many of you may know. Andrew's a bit of a legend in the industry. We are traveling around the country delivering a 2-day course on the structural design for mass timber mid-rise structures. We've done the one in Adelaide, which was really well received. The next one is in Sydney on Monday 6th and Tuesday 7th of April. We'll then come to Melbourne, Brisbane and Perth and any other cities if there's sufficient demand. So if you're interested, let Mariella know, Mariella at TDA in New South Wales, asn.au. Here is Design Guide 50. So go to Wood Solutions, get your hands on it, start to burrow into it, and please provide feedback and comments to us. And I've run on slightly, so we don't have too much time for questions. I apologise, but thanks for listening.
Thank you very much, John. That was fantastic. We actually do have a couple of questions here. Can you see the question screen yourself?
Hang on, Q&A. Yep, here we go.
So we've got 2 questions there. I'll let you shoot first.
Adam, while I'm thinking of the others, can you answer the question if the previous webinar is available somewhere?
Sorry, if the previous question, it will be in a few weeks. So all of these recordings will be up in a few weeks. So for last week's webinar, I accidentally didn't record it properly. So I'll be looking to record it again, and then I'll put it online. So all the recordings of the webinars and the CPD will be available in a few weeks. Take a bit of time to get them going, especially the CPD forms.
I've got a question from one of the participants. What's your opinion on timber concrete composite floors, especially in high seismic regions where the diaphragm forces are very high? Yeah, look, timber concrete composites are really, really interesting. And I'd say at this stage, it's a specialist market. It started historically by people using concrete screeds to upgrade existing floors in things like houses that they were converting into offices in European town centres and stuff. Works really, really well. It's important that we separate the idea of a structural timber concrete composite from the addition of concrete screed separated from the timber structure to improve acoustic performance. They're quite different things. But yeah, timber concrete composites where the concrete is working compositely in compression with the timber, which is in tension, can be a really good solution. And there's a Wood Solutions guide, Adam, I think I'm correct in saying, on timber concrete composites by Xpan.
That is correct. It's one of the guides in the 30s. I'm not sure exactly what one, but yeah, recommend downloading that, the system.
Another question, is this reasonable construction for 7-8 stories in a wind region C, cyclonic? The answer is you would need far more walls internally. To be perfectly honest, we worked very hard to get this building to work with its existing layout, with the number of shear walls we had based on a fairly modest wind load. So if you recall the plan of the building, up and down the screen, we had very little provision of shear walls based on the architectural planning. And this is what I was saying. We kind of received this design as a challenge to say, well, can you make a solution work? We can in a modest wind load. But the reality is that if this was a developer saying, I really want to do this timber frame, it's going to be cost effective, I'm in wind region C, what do I need to do? You as the engineer would need to come back and say, well, look, you know, the wind loads are much higher. We need far more shear walls in this direction, and so on. So on a case-by-case basis, but in principle, it's feasible.
So there's a few more here, John. Maybe take one or two more. I've got a question from John that I might be able to help answer. So John McLean, any detail on existing examples to present to interested clients? Yeah, if you get in touch with us, John, we'll let you know all the case studies around Australia and then also overseas that you can really help build the case for your interested clients, plus with some costing backgrounds and whatnot.
Another question here about axial shortening. How do you manage connections when you have concrete core, given that they move in different ways? And that's a really good question. It's not an exclusive problem. Sorry, it's not an issue exclusively to timber, where we have concrete cores and steel structures, particularly over large scale buildings. We need to be really careful about thermal movements in the steel during construction, where we have big buildings, and concrete movements over time. And it's just about really trying to quantify how much movement we're expecting over time, acknowledging that it's an estimate, and then coming up with robust detailing to deal with that, and then monitoring during construction just to make sure that things are going as we expect.